Okay, so welcome to day N-1, because we will meet whenever our exam time is. I guess it's 8 o'clock on Friday, isn't that blast?
8 in the morning?
Yeah, I think that's when the exam time is. So there's a reason for you to do the evaluation.
You did that last class yesterday.
What else
Like,
are the
it's twice.
behind it? Are they officially in the class or something? You need to contact them and get them to do it.
Assuming that they're watching it, you know what, I'll send an email around. But I think they're watching the recordings and they show up, so, they'll see what I say. Let's, for next week, a couple of announcements. First of all, the math in is tomorrow from 10 a.m. to 5 p.m. I know that, a lot of you probably don't need any help per se, but, this is a good way to kind of polish up your teaching in a fun way, and there'll be pizzas and so there's that. The math club will take place today at 5 p.m. We have an undergraduate who actually did an internship at Sanford, I think. Anyway, he did sports analytics. A lot of people kind of dig on that, so that'd be a fun one too. So next week, we'll meet during our exam time. I will not talk for 2.5 hours. And of course, if 8 o'clock is too much of a burden, then I will record this because I've actually become sort of obsessive about such things. So there's that, and office hours. I've got a very busy week that week, which I hope implies that I will have enough busy week after that. We'll see. Let's do this. Monday, 7 a.m. So I'll be in my office all day on Monday. For if you need to see me on that Monday, just ain't gonna work out for you, let me know and we can set something else up, because I will have breaks in my schedule. I've got some weirdo things to do that week and it's still a little bit in flux, so. That's not. Okay, any questions? All right, so the last thing we had was this result where if you have a unit in a quasi-local ring, then there's some integer k, so such that every sum of the m-1 powers is a unit in R if m happens to be relatively prime to k. So we're going to apply that to the next theorem here. Theorem 625. Suppose R is a domain and R is the intersection of finitely many valuation overlays. So suppose R is a form Vn, where each Vi is a valuation overlay of R. And of course, let me point out that implicitly this means that that R has to be an integral domain because it's an intersection of integral domains. Then each Vi is a form R localized at some Pi for some prime ideal Pi and R. Additionally, R is a Bezier domain. additionally, R is Bayesian. So every finitely generated ideal is in fact principal. And if no pair of the valuation domains are comparable, no pair of valuation domains, VIPJ is comparable. If I find J, then these PIs are precisely the maximal ideals are. So when you have a domain, so actually this tells you something about intersecting valuation domains. So, you know, think of this not just, okay, at random, I'm gonna find this artist, and just think, okay, I'm gonna form a domain R by intersecting these valuation domains. Then in this R, each one of these VIs is of this form R localized at PI. Right, by the way, if that's true, that already shows that R is proof domain, correct? Because, right, this all, because this basically this shows that these are the that are localized at every maximal ideal is in fact a valuation domain. The next statement strengthens that observation. It is proof of by saying, hey, not only is it proof of, not only are the finitely generated ideals convertible, but principal. And if none of these valuation domains are comparable, then the PIs are precisely the maximal ideals are, right?
When you say the PIs are precisely the maximal ideals are, do you mean some of the maximal, not like exhaustively, or?
No, exhaustively.
Because then why could we not have an intersection of fewer PIs then, and then fewer corresponding maximal primes? I don't see what in the definition requires us to have all of these PIs.
Let me make sure I understand your question. So what your concern is, there might be more maximal ideals?
I'm saying, we're saying this R of this form where it's the intersection of valuation overrings, and then each of these valuation overrings corresponds to a maximal ideal. This R localizes some maximal ideal. How do we know that we're getting all the maximal ideals? Because it doesn't seem in the definition like we're saying that this number of these is important. Like, why couldn't it just be the intersection of 2 or 3 or 4? Are you asking?
Well, it is. So, for
Yeah.
example,
Kind of.
if R is just V1 itself, then there's only maximal ideal, right? If R is If R is V1 intersect V2, then there's 2 maximal ideals unless V1 and V2 are comparable. Because if, for example, V1 contains V2, then this intersection is just V2, right? And then there'd only be 1. And so, what we're gonna have to do is kind of look at some elements. So let me give you a notation. If QI is maximal ideal of VI, then we'll define PI the QI intercept R, as you might expect. And notice my wording is right, because notice that QI is, in fact, let me sort of glossed over it, but let me say QI is the maximal ideal, because of course any valuation domain has only one maximal ideal. Then I am going to let PI be QI intersect R. Of course, this will be the prime ideal of R automatically. And I claim that these are the primes that we need. We show that VI is equal to R localized to VI. Okay, so that's gonna be our task here. So to this end, notice that it's easy to show that our localized PI must be contained in VI. So the other containment was interesting, so let X be in, let X be in VI. We want to show that there's an S. Show there it's an S and R not PI, such that SX is in R. And this will do what we wanted it to do, because that will mean that X is an element of R divided by an element of S that is not in PI, right? So then X will of course be an R localized to PI, by the definition of localization of PI. So, for each VJ, so here's the way we're gonna set about this. For each VJ, such that X is in VJ. Now, of course, X is an element of VI, so it's in the quotient field. This X may or may not be in the other V's, right? Maybe it is, maybe it isn't. But let me point out, before we go much further, that either X is in VJ or its inverse is, right? Because each of these VJs is evaluation rate, right? So X is either there or its inverse. So for each X VJ, such that, actually, I want to further, such that X I'm going to start with units here. We're going to use this previous result. We find a corresponding KJ. As per theorem 624. And this means that for all MJ such that GCD KJ MJ equals 1, is a unit. Okay, so that's what I mean by that. 64, wasn't it? Yes, okay, good. It was 64. Okay, so now we define technical difficulties here. There we go. Cursed chalk. Okay, so now take M greater than or equal to relatively prime to all KJs. And we're going to take M equals 2 if there are no KJs, right? So, I mean, I guess it is possible that none of X is not contained in the units of any of the others. In that case, we'll take M equals 2, right? Now, let S one plus X square X M minus one inverse. I'm going to define S to be this way. And this S works. That is to say, S times X is in R. And so let me go through a couple of cases to consider about this. Number one, if S is in QJ, I'm sorry, if X is in QJ, if it happens to be in the maximal ideal of VJ, then S is a unit. Right? Because if X is in QJ, it's in the maximal ideal. And so one plus this mess is a unit in VJ, and so its inverse is a unit as well. Okay, number two, if X is a unit in VJ, suppose that X is a unit in VJ, then S is a unit in construction. In fact, this is a crucial reason why we set it up this way to work out. So what this does here. And of course, finally, the case that we really must consider is what happens if it's not in VJ, right? So in the first couple of cases, we've covered what happens actually if X is in VJ. I claim this works even when X is not in VJ. So what happens in this case? If X is not in VJ, then, as we observed earlier, so look at the inverse of X, call it Y, right? We know that Y is in VJ, right? Because these are all valuation domains, and actually I can see something slightly stronger. What can I say? It's a little bit stronger than this. Not only is it in VJ, but it's in QJ. It's actually the maximal ideal. It can't be a unit because otherwise an X would be in there. So X, Y is actually in the slightly stronger statement. It's in QJ, and in this case, work out this computation. It's actually a little bit fun. S equals Y to the n minus 1 over 1 plus Y. And here I claim that actually in this case, S is actually in QJ. And the reason here is as Y is in QJ, this chunk, so it makes sense for me to do this chunk because this chunk right here, Y plus Y squared, this is all in QJ. So 1 plus this is a unit. right? And so this is Y to some, at least first power of something in QJ, so this S is actually in QJ as claimed. So in all cases, what we have is S is in VJ. Now, since X is in VI, we have that S because remember, this is how we picked S. We picked it to be in R, but not in PI. So particularly, in particular, S can't be in the maximal ideal of VI, so it's a unit in VI. And so S is not in PI. Because PI is the unit, is the intersection of QI with R, and it can't even be in QI because it's a unit. Right. Well, so to finish this, we have that S is where I claimed it was. We just need to show that S is in fact, that is to say S times X is in fact in R. And that's kind of the end game for this. So to show this, of course, it suffices to show that SX is actually in every one of these valuation overrings. And for this, only worry about case, right, where this situation happens. But in this case right here, we see in this case, SX here. Well, when you multiply this by X, it's the same thing as multiplying by Y inverse. So this is Y the n minus 2. N minus 1. And this is again still in VJ or NJ. And again, this is because this thing is a unit and Y is in there. So notice, of course, that we're saved by the fact that my M here is at least 2. So worst case scenario, this is 1 divided by a unit, right? Okay. So we have shown that each VI is R localized. We've got that under wraps. And so now what we can do is we can shorten this to an irredundant representation. we can now we're done. Valuation domains. So, for example, if VI is if VI is contained in VJ, right, because VI intersect VJ will be VI, and so intersecting VJ with everything else doesn't do anything. To obtain V equals RI. No, get this all turned around, and now R equals intersection of VI with no two VI's comparable. Everybody okay with that? So now we can take our so we've gotten our representation in the first place. Now we've noticed that if you've got extra valuation domains, you can throw out the ones that contain other ones, right? Actually, if you have an infinite intersection of valuation domains, you've got to be a little careful about this. The finiteness actually helps us here. So if we suppose that we have this representation as irredundant in the sense that none of those valuation domains are comparable, then P1, P2, Pn are precisely the maximum yield. And R is a semi quasi-local proof domain. Because when you localize at any of these maximum deals, you get a valuation domain as per what we did before. And if you have a semi-quasi-local proof domain, remember any invertible ideal over a semi-local domain or a semi-quasi-local domain is principal. This means that every finitely generated ideal is principal. And so it's crazy. Okay, any questions on that? I'm going to do a different proof actually. My notes on this one. So, oh, by the way, any questions? Let's suppose A and B. Well, actually, I don't say this. It might be sort of implicit, but I want R to be a domain here.
So, in general, for a domain, the integral closure for a domain R is the intersection of all the valuation over rings between it and its diffusion field fractions.
Right.
So in the last theorem, I think when you find it, what was confusing, we're supposing that R is equal to this intersection of these VIs, where each VI is a valuation over ring of R, which would seem to imply that R should contain its integral closure.
R is interval closed. Any such R will be interval closed.
Okay.
Yeah.
But I guess, how can it? Wouldn't, so we take a subset of the VIs that we use. Oh, that's why I was getting confused, because then you just redefine, I guess, what your R is. Oh,
Yeah,
okay.
right,
I-
right.
that's
When
what I
I throw out these valuation domains, it doesn't change R, right? But if you throw out, some VIs, actually, what will happen is if you start plucking off the VIs, you will get intervally closed rings that contain it. Now,
Yeah,
if it's
okay.
not redundant, it won't be an interval extension, it'll just be another interval closed ring that contains it. Okay, so, right, let R be a domain, that is quasi-local and one dimensional. So the variable domain, therefore zero is a prime ideal. So of course, one dimensional means that every non-zero prime is maximal. Quasi-local means there's only one maximal ideal. So in particular, there's only one prime ideal. Agree? Because take two prime ideals, P and Q, that are not zero, is quasi-local, they have to be the same, right? So, if A, B, and R are non-zero non-units, then some power of A is divisible by B. By the way, my choices of A and B are arbitrary, so that also means that some power of B is divisible by A, right? So obviously, this is a strong statement to make about a ring, right? I mean, given two integers, 3 and 5, that are not zero and not units, I don't expect the power of 3 to be divisible by 5, right? So proof. Yeah, I did a correct proof in my notes. I'm doing some crap with zero, but I just didn't care. Let's do it this way. No. Since R is one dimensional, we have there's only two prime ideals, the zero ideal, because it's a domain, and because it's one dimensional, there has to be more than one prime, it has to contain zero, and since it's quasi-local, that's it, right? This is an exhaustive list of primes. So by hypothesis, A and B are both in M. But not zero. Correct. Now, can somebody explain why a power of A is in this? Check this out. All right, so, notice that, now, note that the radical of B is the intersection of all the prime ideals that contain B. And there's only one of them, right? This is M. Therefore, A to the N is in the ideal and then B. Right, so A to the N equals RB. R and R. Therefore, B size A. Okay, any questions on that? Okay, let me give you a quick definition. This is actually important. There's a lot of interesting work done on this kind of, sometimes it's called finite character definition. We say that the intersection of a bunch of valuation domains, actually, I don't even care for valuation domains. They can be something else, but we say, well, let's do it this way. If suppose you have R as an intersection of some collection of domains. Now, I'm only usually think of these as valuation domains, but there's no reason that you couldn't think of this as something else. Domains with a certain property. Usually, again, it's an intersection of valuation domains, but I'm not going to state that. We say R is a locally finite intersection sometimes it's maybe specified. If, by the way, has anybody ever heard this definition before? For all, let's say if every X and R minus 0 is a non-unit and only finitely many so is a unit in all, but finitely many. So what it means to be locally finite is, and in fact, let me think of this in terms of valuation domains here. But again, you could do something a little bit more general if you like, domains with certain properties. For valuation domains, think of it this way. What this means to be locally finite is every X and R is in every one of those valuation domains, right? It's a locally finite intersection if it can't be contained, if it's not in the if it's in only at most finitely many maximal ideals of these. So in other words, for sort of most of these, all but finitely many, any X is not in this. Let me give you an example. I'm going to illustrate this here. I'll give you a positive, I'll give you an example and a non-example, if you will. Of course, Z is the intersection of Z localized at P for all non-zero primes, right? There's a number of ways you can see this. We actually had a theorem that said if you have no theory in every closed domain, then this is true as you intersect over the height one primes, and that's exactly what this is. And also you can appeal to a much earlier result because that list of the Z localized at P are all the maximal ideals, right? So this is basically that result that R is the intersection of R localized and M for every maximal ideal. Now, Jerry, give me a positive integer bigger than 1.
37.
What's that?
37.
Okay, he picked a good one. 37 is and the unit and all others. Right, because it's relatively found all the others. 420, which is 2 squared times 3 times 5 times 7, I guess. Is
A good pick.
yeah. Well, it's got all those nice primes. That's right. It gives me how like.
That's true. 2 times over 2 times.
This one is a non-unit in all these valuation domains, right? In fact, in this one, and this one, it's actually equivalent to the generator, right? In this one, it's equivalent to 4, right? But it's buried in all these maps, in these finitely many. And all the primes that aren't this list, it's a unit, right? So this is an example. This is you're intersecting infinitely many valuation domains in this case, but it's locally finite because any integer other than 0 is contained in only finitely many of them. I mean, even 1 is contained in none, right? Let me give you a non-example. This is like the 3rd time I think I've used this example. You remember how you can take, you could start here that has a PID that has only 1 prime, right? So you might start here at C localized at 2. You can now split this into 2 different primes, right? So you start here with P, and this becomes Q1, P1, becomes Q2, P2, becomes Q3, P3, Q4, 4, and right. Now, this turns out to be, as we've talked about, so your maximal ideals all the way up, these are actually primes. So you can build these things so that this remains prime at every stage, this remains prime at every stage after it's created, and so on. All right. Notice that P was prime at the sort of the 0 stage, but it's no longer prime because P is this times this, P1 is this times this. I'm sorry, P1 is this times this, P2 is this times this, and so on. Everybody okay with that? All the maximal ideals are principal, except for this one. This maximal ideal here is not principal. Right? Let's call this domain R, and R is equal to, and let's call this maximal ideal M. Like that. Right. In fact, I've argued that in fact, this is what we call an almost dead end domain, so it's integrally closed. It's in fact, the intersection of, well, these are all maximal ideals, so there you go, R is the intersection of all these. Okay, so far. But this is not a locally finite intersection. Because in our local as Q1, this is the generator, and this is relatively prime to this. So actually, P is equivalent to the generator here. And our localized up here, this is the generator. So these are the same. Right. Yeah, they're real. So in fact, P is not a unit in this one, it's not a unit in this one, it's not a unit in this one, and so forth and so on. And in fact, this is true for any of these P's along here. So for example, this one right here, it's not contained in these two maximal ideals, but it's contained in this one, it's contained in this one, it's contained in this one, and it's a non-unit in every one of these maximal ideals, including the big one. Right? So this is sort of another example. This one is not, this one, when you look at that intersection that I gave you there, that is not locally finite. Okay. So I will give you kind of these. I'll give you this last theorem. I don't know if I've got time to finish it up, but. Or this. Typo. What a surprise. Theorem. Yeah, in your notes. This is definition 629. There's probably not a definition since I proved it. So let the domain R be an intersection of one-dimensional quasi-local overlays R. This is an intersection of locally finite. Is a quasi-local. Rings of R, and the intersection is locally finite. So so let QI be the maximal ideal of VI. Of VI, and PI as before, be the intersection of that now with R. If N is a non-zero prime ideal, then N must contain PI or some I. Okay, any questions on that? I only just finished the notes by 7 lines, actually, it looks like. The proof of this is actually fairly straightforward. So take a look at it, let me know if there's any confusion. We'll meet again Friday, and I'll do a little kind of, just kind of a fun day, I hope. I hope most of these days have been fun. I really enjoyed, having you. I'm sorry that I dragged my feet so much on the homework, but you will get it all back, feedback and all that thing. Any questions? I guess I don't have to tell you all this, but once my student, always my student. If I can be of any help in the future, let me know, and y'all have a great Christmas, holiday, whatever you celebrate.